Yeah, welcome back to our exploration of amplitudes from the nodal sphere. What I thought I'd do today for you to help you catch up with what we did last time is just briefly recap where we got to. So in the first lecture, we discussed a formula, the CHY representation for massless amplitudes, and we saw that that lives naturally on a Riemann sphere with punctures. And so what we did last time is we constructed the world-cleat model underlying this, which is the ambi-twistor string. And if you remember, we constructed it with a bare action term that captures the basic correspondence, which I've reproduced here. And then we had some meta term, which gives us the different models. And in particular, we found that gravity comes from or supergravity comes from an RNS-like model with two fermion systems that I've added here. And then in the main part of the lecture, what we did last time is we calculated correlators, endpoint correlators in this formalism. And what we culminated with was reproducing the CHY formulas from the ambi-twistor string correlator. So that was the highlight of our calculation last time and what we were working up to. And so what we're planning to do today is actually extending this to one loop. Now, just because last time was a bit technical, I thought it would be really good for us to actually briefly pause and recap what the main elements in this calculation were that we saw yesterday. And if you want, this is my cartoon of what we did last time. And what we found is that, as expected, the gauge field E, our Lagrange multiplier for the chiral stress energy tensor, gave us the integration over the chiral part of the moduli space M naught n. Whereas E tilde, remember in our action, E tilde is the Lagrange multiplier for the ambi-twistor constraint, for the p square constraint that reduces us to null geodesics, was what encoded the localization on the scattering equations. And this is nice and intuitive because remember how we constructed the scattering equations. They are the conditions that tell us that with punctures, p square is still zero everywhere. And E tilde is indeed, apologies, the constraint that gauges p square. Now, that was in some sense, well, that was what we discussed first. And the main part that we, apart from that, was the px system. Now, there's two parts for this. The x0 modes will always give us momentum conservation. That's easily seen from the action. And in this case, this is actually the effective action, if you want, where I've included the contribution from the vertex operators. And as I said, if you integrate out the zero modes, we will always end up with momentum conservation, which gives us the d-dimensional delta functions over K, sum over Ki. Now, remember, if we're going to extend this to a one-loop calculation, we'll have to be much more careful with what this dimension is. And in particular, we'll always work in the critical dimension. And in particular, that means for the RNS string that we're going to work, RNS ambi-twistor string, that we're going to work with d equals 10. Now, when we then integrated out the rest of the px system, the x integration was very much straightforward. And what we found is that it localizes p onto its classical equation of motion after integrating out p then, which is in particular the constraint that d bar p mu is 2 pi I sum over I Ki mu delta bar sigma minus sigma I d sigma. So this is what we were solving to find the standard equation that we had for p, just as a sum over Ki over sigma minus sigma I. And then plugging this back into the scattering into these constraints here, reproduce the form of the scattering equations that we need. Now, to complete this to an amplitude calculation, the last thing we had to look at were the matter systems, and I've just written the size system here, for which you can check, and you should check, that this reproduces the Pfaffian prime M. Now, all of this is something that we'll have to generalize if we want to move up from tree level to the one-loop calculation. And something that I should stress at this point is that from this point on, we're going to work in the RNS system, just because the type 2 supergravity, the spectrum of the RNS string is just type 2 supergravity. For all other models, we would find some unphysical gravitational mode propagating in the loop, and projecting these out is quite hard. So we're just not going to get into that. It's also not known how to do this in general on the torus. And instead, we're going to just do the calculation in the RNS model. I should also say we're going to be a bit more schematic today, which is also why I reproduced this cartoon for you, just because of time constraints. It would take way more than an hour to discuss the one-loop calculation in all detail. Now, so we're roughly going to follow actually the cartoon that I have here. So the first thing we should talk about is what is the moduli space of the torus that we will then integrate over. And this is something that you've actually seen before, I think, from Claude's lectures and possibly also from Ollie. And so hopefully this is something that you're already familiar with, but just to recap, let us parameterize, or let us encode the torus as usual as a lattice in the complex plane. So I've drawn my two basis vectors here, lambda 2 and lambda 1. And we know that we can always do a conformal transformation, meaning we can rescale and rotate. In particular, we're going to rotate so that lambda 1 lies on our real axis, and rescale such that we normalize this to 1. And then what we'll always end up with is our picture down here, where we only have one complex parameter, tau, left. And then in particular, our lattice is just z plus tau z. So naively, you could say, this is what we should be integrating over. This is Teichmüller space. So all tau such that in tau is larger than 0. But in fact, we do know already from Claude or from Ollie that this is not true, because not all tau generate different lattices. And one way to see this, one graphic way to see this, and very intuitive way, is to look at Dehn twists. So what Dehn twist basically means is we cut the torus along a circle, just rotate once around itself, and then glue it back together. Clearly, that gives us the same torus. And this is something that we can see very easily in this picture that we have. So in particular, there's two transformations that we could do, one cycle of the torus, one the other one. So for one of them, if we just rotate one cycle, in this case, lambda 2 by lambda 1, we can see, let me include here our tau here. My conventions are that tau is, if I remind you, lambda 2 over lambda 1. Then we can see that this naturally corresponds to tau going to tau plus 1. And similarly, we could just do the same thing for lambda 1. And if we follow the correspondence through, then this just corresponds to tau going to tau over tau plus 1. Now, this is a nice geometric one, but in fact, it's often simpler to work with a different transformation, which is we often call S, which sends tau to minus 1 over tau. And I've just given you here, you can check that B can be expressed in terms of S and T as given. Now, if we put this all together, we can actually see that we should identify tau with any other combination that is related to the original tau by PSL2Z, which we often call the modular group. Now, if we now think about what this means, what we should integrate over, we find that we should integrate over the fundamental domain, which I've shaded here. And to see this is easy, so we know we should integrate over tau just in the upper half plane. But in addition, we have the quotient by tau going to tau plus 1, which we can see gives us that we can restrict the real part of tau to lie between -1/2 and 1/2. And let me just correct. This one should read not tau. And the other part is that we know we can send tau to -1/tau, which you can easily check that we can use this to restrict the integration domain to mod tau larger or equals than 1. Okay, so this tells us what we should integrate over. Now there is something related that we should talk about, which is new at one loop that we didn't have to deal with at tree level. And those are the spin structures. Now at tree level, we only ever had one spin structure, so we didn't touch on this. But starting from one loops, this is something that will play a big role in the matter correlators for the fermions. So let me just remind you for what the spin structures are. Now, on any higher genus surface, we can use a homology basis of cycles. So we'll have an A cycle that I'm sketching here, and a B cycle, and we want to choose them such that the intersection number which I've just denoted here by this hash is canonical, so that they just intersect in one point. Now on the torus, this is simple, but there's various choices at the higher Riemann surfaces that are more or less convenient for it and give you different parametrizations in the end. And in particular, in the end, we want to end up with something that remains invariant under whichever choice of basis we picked for this. Now at genus G, we can then see that there are 2 to the 2G spin structures, depending on whether spinors pick up a sign if they go around these cycles or whether they just remain the same. And it's often useful to classify these into even and odd, where what we mean by this is that we count the number of zero modes of the spinors and calculate them mod 2. Now, our notation for these spin structures will always be that we take alpha to be alpha prime, alpha double prime, where both of these are just vectors in Z mod 2Z, so just 1/2 or 0, to the G, where G is the genus. Now, in particular, at genus 1, we'll then have, if you just calculate this out, 1 odd spin structure and 3 even spin structures. And I'm going to denote my odd one with alpha 1. This is standard notation. And the even ones with 2, 3, and 4, where we can read off from here, from the alpha prime, whether we have an S or in a Ramon state propagating along the B cycle. That is something that we're going to use a little bit later. Now, something important to mention here is that modular transforms, meaning tau going to tau plus 1 and tau going to -1/tau, permute these even spin structures, just the even ones. And I've given you here how S and T act on the various spin structures. In particular, that means if we want to have something that's invariant, and we really just integrate over the fundamental domain in the end, we know that we'll have to find something like a sum of the spin structures. This comes out of the standard GSO projection, similar to the RNS string. So this will guarantee for us that we end up with something that is modular invariant. Now, I've given here the signs that are required, and the 2 signs here, the plus minus, just corresponds to whether we're looking at type 2A or 2B. In particular, only the signs among the even ones are fixed by modular invariance. Now, the other thing that I want to mention is that we won't actually need to look at Z1. for two reasons. Eventually, we're going to look at how this will end up on the nodal sphere and look at this in lower dimensions. And in that case, this will never contribute. And if you want to be genuine about the torus, you could say that we only look at the 4-point amplitude. And for the 4-point amplitude, just by zero mode calculations, this also drops out. So that's going to be my reasoning for restricting to just the even ones. If you're interested in the odd ones, I've included the original paper that calculates it in the reference list, and you should feel free to explore that. Now, last in this preparational mode is that we should briefly look at what objects we encounter at genus 1 and on the torus, just because these will play an important role in our CFT calculations. Now, the first thing to notice is that in contrast to the sphere, we have a holomorphic differential on the torus, which is just dz. And in general, for higher genus, there would be g such differentials. Now, the other important object that we'll need, or the other two important objects, are the Jacobi theta function, which you've seen, for example, for all of these, you've met them already in Ollie's course. But I've given here the definition again, and I should say that that I'm using q equals e to the 2 pi I tau. Now with this, for the odd spin structure, you can calculate the prime form, which I've given you here. And in particular, note that the prime form looks, when z goes to w, locally like z minus w over 2 pi I with the same factors of dz to the minus 1/2, dw to the minus 1/2. Why are these so useful for us? Well, we can construct two important objects that appear everywhere in the CFT calculations from those. One is the Ziegler kernel, which we'll see in a minute that this will play an important role in our fermion correlators in the psi-psi 2-point function. And locally, this looks like we expect it to look. So locally, this looks like, you can easily check that as z goes to w, this looks like 2 pi I over z minus w dz to the 1/2 dw to the 1/2. And the other important object is the Miramorphic differential, which you can construct out of the prime form. And locally, around each point, z1 and z2, this just has a simple pole with residues plus and minus 1. So this looks like minus 1 to the a dz over z minus za. Just to be precise, or to make precise what I already said in words, the reason we'll need these is that on the torus, we have the following Green's functions. For the fermion system psi-psi, we find that the 2-point function in the spin structure alpha is just given by the Ziegler kernel alpha with the points z and w is given. And for the XP system, the 2-point function is independent of which spin structure we're working on, but it's given by this Miramorphic differential z. And z0 here is just a reference point. Now, the other point that we're going to need is we'll need to know what the partition functions are. And in this case, I'm giving them to you for a general beta gamma system, which with h beta again is just our conformal weight being lambda, and h gamma then correspondingly being 1 minus lambda. Now you can calculate these. This is a standard calculation. You can find them in any standard textbook on string theory. So for example, if you're not familiar with this, you can look this up in Polchinski. And what we find is that the partition function on the torus is given in terms of the theta functions, the Jacobi theta functions for the spin structure alpha, and the Dedekind eta function, which I've included the definition down here. Now, just from this, we can already put together what our ambitwistor string partition function in a spin structure alpha will be. And let's do that. So we find that we have from our PX system, we find a 1 over z1 to the 5 from our psi system. We find a z to the 1/2. Let me see what my notation was. 1/2 alpha to the 5. And then from the various ghost system, we find Z0 from the BC system, and sorry, this is, yes, and Z3/2 from the beta gamma system. So note that I've calculated a chiral here. So I've split the PX system and everything into 2 contributions, so that it looks like we have 2 chiral contributions. Now, putting this all together, what we find is that this becomes theta alpha to the 4th, just calculating the front part here, divided by eta to the 12th. Okay, now if we actually calculated what the full amplitudes become with the sum over spin structures and everything, we would find by some standard Jacobi identities that just for the vacuum partition function, this vanishes. And that's good. And of course, what we should look at are amplitudes with vertex operators. And the first one that turns out to be non-zero is the 4.1. So what we're going to sketch now is how to actually calculate this. I put here n, but if you want to think about this with just 4, that's also completely fine, 4 punctures. Now, the first part to notice is that what I've written here is the fully gauge fixed. Everything is fully gauge fixed already. So in particular, I've used here already our gauge fixing for E. So everything concerning E is already taken care of. So we're integrating over the moduli space M1n, including in particular the fundamental domain for d tau that I've written here. And then for E tilde, I've chosen the gauge fixing that we discussed last time, but adjusted for the torus. In particular, I've split this into, so for the torus, we have the basis, the dimension of our cohomology is n, but we're only free to choose n-1 of these to extract residues in the end because of translational invariance on the torus. The other one will always be determined by these types of Beltrami differentials. So I've included an additional Beltrami differential, and we'll see where this comes about in a second from a slightly different perspective. Now, what I'm trying to say here is I've already done sort of the E and the E tilde part secretly on the side. So what we're left to do is the PX system, and the easy part is the zero modes, and we can see that the zero mode calculation didn't depend on whether we were on the torus or the Riemann sphere. So in particular, this gives us again the 10-dimensional delta function encoding momentum conservation. Now, the difficult part is clearly what to do with the rest of the PX system, but we can choose to use the same trick that we did last time. Remember, what we did was just to notice that nothing in the vertex operators except for the exponentials depended on x. So we could choose to take them into an effective action and then integrate out. The x system was trivial, and we saw that P just localizes onto its equations of motion. So for the non-zero modes, none of this depends on whether we're on the torus or the Riemann sphere up to the point that I've just said. So we can repeat the same trick and find that d bar p mu is still 2 pi I sum over I equals 1 to n ki mu delta bar sigma minus sigma I d sigma. This is the same condition we had yesterday. Actually, let me be a bit more, let me stick to the notation z minus zi here. I'm trying to stick to the notation of using z's on the torus. It will become clear before the end of the session why I'm trying to be careful with this. Okay, so this is the same as before. The only new thing is that we now have to solve this on the torus instead of on the sphere. So we know what the solution on the sphere would have been. It's just ki over z minus zi. On the torus, there's two new things that we have to take into account. Well, first of all, it's clear that 1 over z minus zi just doesn't solve this anymore in the torus. Instead, we should generalize this over I equals 1 to n ki mu to these Miramorphic differentials that we were discussing, zi and then some reference point z naught of z. The other part that we have to generalize is that on the torus, we now do have a homogeneous solution. And we'll have to include that as a, if you want, zero mode parameter, which is everything that is proportional to dz, our holomorphic differential. And so I'm going to suggestively call this L mu, our zero mode parameter. And let me remind you, this was the holomorphic differential. Okay. But what does this mean? We now want, for our scattering equations and the delta functions, remember, we have, again, the delta functions in the vertex operators that we want to impose. I've already hinted at that we have the freedom to choose n minus 1 of these with the same choice as last time to extract the residue. So let's do that. So let's choose Beltrami differentials to extract the residue, and we can do this for n minus 1 of them, such that integral over mu I p square just becomes the residue at zi of p square. Now, that gives us n minus 1 of the scattering equations, which will now look like EI1 is the residue at zi of p square. Okay, let me. And we will find that if you calculate this out, this is just 2ki dot p of zi, which is useful to do. Now, note, however, that the dimension of our cohomology group is n. So we can only choose n minus 1 of these because the last one depends on the others. This is not an independent one, so it doesn't give us a basis. So we have to choose one more Beltrami differential, and there's various things you could do. So for example, you could just choose to set this, to set p squared to 0 at an arbitrary point that you pick. However, there's a slightly more invariant choice that you can make, and that is that you can see as follows. On all of these other scattering equations, we can write p square always as some function u that will depend on everything. In particular, this will depend on L, this will depend on the other momenta ki, and will depend on all the marked points zi times dz square. This should be clear because we've set all residues to 0. So the only part of p square that is left is the part that is proportional to the holomorphic differential square. So this is on the support of the scattering equations. So then it is convenient to choose our last Beltrami differential such that we just set this function u to 0. So E1, and I'm going to call this not because it's our last one, is just u. Okay, so that takes care of that part, and we've now done the PX system. Now the only other part that we need to do is to calculate out what our worldsheet meta system, in this case this is our psi system, and the psi tilde system gives. And it's clear that this will again give Pfaffians, and it's hopefully also clear that these will be Pfaffians that involve in particular these as alpha here. I encourage you to look at this, but it's not a difficult calculation. It's a straightforward generalization of what we did at tree level, or what you hopefully should check by yourself at tree level. And if you put this then all together, we arrive at the following answer. So again, let me remind you, this is for even alpha, so we don't need to take care of the fermions of the psi system. Now, we've seen the momentum conservation come out. The integral over L here is just from, as we said, the 0 mode here. So in particular, that's something that we will have to integrate over. And then the rest, this part is what we were just discussing before. This is our standard measure. We find the full localization that we just derived on the last slide. And then the integrand here is what I said comes out of the psi system, just some Pfaffians summed over spin structures here. And I believe I am missing a factor of Z alpha, Z beta for the partition functions that we calculated. Okay, what are these M alphas? They're the same type of matrices that we found at tree level. Remember, our M had the same form, A minus CT CB. But here the alpha now indicates that we've evaluated this in the spin structure alpha. And indeed, we see that this has the effect of replacing the 1 over sigma I minus sigma j by the Zego kernel between the punctures Zi and Zj. Now, note that this is a full Pfaffian, not a reduced Pfaffian. And it's easy to check that there is no kernel here anymore, basically because CII becomes now just epsilon I dot P. And the Zego kernels are not directly related to what appears in our scattering equations here. Now, I will often call this bit here the integrand, and I'm a different notation for I. I know it's a bit inconvenient that all of these things are called integrands, but hopefully by carefully distinguishing the notation, it should be clear what we're talking about. Now, there's two comments I want to make here. The first one is, note that something does generalize straightforwardly from tree level here, which is that IN1, our full integrand, is still fully localized. Let's count this together briefly. So we're integrating over the moduli space M1n. In particular, that means we have our modular parameter tau here of the torus. And then we have n-1 punctures, because as I said, we have the rigid translations of the torus, and that allows us to fix one puncture on the torus. So in total, that gives us n variables. And if we count the number of scattering equations, indeed, we find the one scattering equation delta bar u that was special, and then the n-1 scattering equations where we again extract the residue at the marked points. So n variables we're integrating over and n constraints. So the integrand, what I've called here the integrand, is still fully localized. We still afterwards have to do the integration over the loop momentum though. Now the other part, which I would like you to check, is that this is still modular invariant. It's not a hard calculation, but you can check that we still find modular invariance under, so this means in particular that this is invariant under tau going to tau plus 1 and under tau going to minus 1 over tau. The tau going to tau plus 1 part is fairly straightforward to do. The tau going to minus 1 over tau, you will see that you have to send dz to dz over tau, dz over tau, and in particular, the loop momentum will have to transform. So in particular, you'll find that L will have to transform as tau L for all mu. So only the full integration, including the measure here, is invariant under modular transformations. Now, this is a remarkable formula. Certainly, when it was first derived, was certainly unexpected that you could write field theory integrands as something that comes from a torus, even if it's just for maximal supergravity. And it's tantalizing how close this is to string theory. But on the other hand, if you wanted to calculate with this, this would be really hard. And even if you say you're just interested in structures, no need to calculate, it's hard to see even basic properties like that the whole integrand that you're getting here is a rational function of the momentum. In particular, let me stress why this is so hard to calculate with. If you look at what the delta functions look like, they now depend all over the place on Jacobi theta functions. And you could imagine just solving this. In fact, you can try this yourself. And even at 4 points, this is really hard to do, let alone at higher number of particles. But on the other hand, we do really expect something simpler to come out of this. And what we're going to do for the rest of the lecture is actually see where the simplification comes from and finally make contact with the title of the whole lecture series. Okay, so how to answer these questions, and in addition, already end up with something that you can actually calculate with and that you can use, actually it only relies on a really simple idea, which is to use the two properties that I outlined, namely that we have modular invariance and localization of our integrand in1 to do a residue theorem in the fundamental domain F. So in particular, let me go through what this means. We start out with, let's say we solved all the other scattering equations, and there are the I scattering equations here, that's just the residue I of p squared. So we're only left with one integral in tau. That is what I'm drawing here in my picture. And we will then have a bunch of solutions here from our last scattering equation that we should all sum about. So these should be thought of as solutions to u equals 0 on EI1 equals 0. Now we could then just apply a residue theorem and wrap the contour around. So instead of summing over all of these solutions here, we will then find a contribution over, if you want, the boundary, because there's no other poles of the integrand. And it should, however, be clear that there's nothing coming from here, because the two will just cancel out. Also nothing coming from here. To make this more precise, you can notice that the integrand has no pole on these boundaries. So the only pole that we find is the one at tau going to I infinity. And so that is the only contribution from the full integral that we pick up. So let me be precise. If we have a generic point down here, this would look like a torus. up here, the tau equals I infinity corresponds to pinching one of the cycles of the torus. And if you pinch a cycle of the torus, that is completely equivalent to just working on a Riemann sphere with two additional punctures that I'm going to call sigma plus and sigma minus that you've identified. So the tau equals I infinity geometrically looks like this. Now that's going to be the main idea, and we're just going to spend the next 10 minutes or so fleshing this out in a little bit more detail. So to actually see this at the level of the formula, which I've just done graphically right now, let's do the following. I've redefined for convenience. So I've put here in gray the definition of our integrand that we started out with. But let me, for convenience, just condense the notation and just keep the parts that we need. So I've put in a new I of q here that contains all my delta function, all my in, but also some factors of 2 pi I. And I've also switched notation to q, remember, is e to the 2 pi I tau, which is where my 2 pi I factors come from that I've absorbed into this I of q here. Now, what we can then do is we can apply the residue theorem that we just talked about. Remember that d bar u here is just a del bar where we localize just on the 1 over 2 pi u. And so if we swap the contour around, the only other pole that we pick up, because there's no, on the support of the scattering equations, there's no other pole here that we can pick up. The only pole that we have is the dq over q. In particular, on the support of the scattering equations, all the other poles in here that are potentially of the form zi minus zj for generic kinematics, they're not supported. They're not poles. So when we swap the contour around, the only pole that we find is the one at q, the one that I've made manifest here in the integrand. So that means we're left with m minus m1n dq delta bar q, and then the iq over u. No, but then it is straightforward to actually evaluate this integral because q, I mean, we can trivially integrate over delta q for q equals 0. And this is just minus, as we argued, m naught n plus 2, the nodal sphere with the 2 additional mark points. With now I naught, remember this carries all my measures now, over u at q equals 0. And there's one last step that I want to do here, because we can now actually evaluate what the u is. Remember, u was defined by p square is u dz square on ei at one loop. But on the nodal sphere, we know that dz square just picks up the poles at the 2 nodal points now. So that means that on the nodal sphere, we have u at q equals 0 is L squared just by extracting double pole, the coefficient of the double poles. So plugging this in, what we find is that our integrand becomes of the form minus 1 over L square m naught n plus 2, and here we just have I of naught. So basically all we need to do now is explore what this becomes. This I, remember, is this whole combination up here that I have, the scattering equations and the integrands. We should now see what this becomes in this massively simplified form. Let me stress that we've not performed a cut or anything here. In particular, L square is still non-zero. This is a full equivalence. We've just applied a residue theorem to simplify the formula. In string theory, you would find similar formulas, but only on the cut, only when you send the internal momentum to be on shell. Okay, so let's actually simplify this formula. And the first thing we should do is we should map our parameter z that we had on the torus to a parameter sigma that then now more naturally lives on the Riemann sphere, so that this actually becomes a type of formula that we can then recognize and know how to deal with. Now, the way to do this is it's going to be the following map. Consider the map where sigma is e to the 2 pi I z minus tau over 2. Now, the first thing to notice is that in general, we will have the following domain for this. We have e to the minus pi im tau is smaller than equal than absolute value of sigma, and e to the pi im tau on this side, which is hopefully clear just from the explicit form of this and using the fundamental domain of the torus. In particular, and we identify, q, a sigma, with q sigma due to the 2 pi I tau there. Now, as q goes to 0, therefore, we recover the full sigma in CP1. And in particular, the two punctures we identify under this identification here is sigma plus is 0 and sigma minus is infinity are identified. So in my picture here, my map here is a very simplified map where I've chosen the particular gauge fixing that sigma plus is 0 and sigma minus is infinity. Now, let's see what this does for the important objects that we find in our scattering equations and also that we will see afterwards in our integrand. And the first thing to look at is clearly dz. I've told you this already, and we've used this to extract the residue, the coefficient of the second order pole of p square already. But if you calculate this out, what you find for dz is that it just becomes 1 over 2 pi I, 1 over sigma minus sigma plus, minus 1 over sigma minus d sigma. And I will often call this whole bit here omega plus minus of sigma, in slightly leaning on the higher genus notation, but it's going to be something that a shorthand that will come in useful. We'll see this combination pop up all over the place. Using this immediately, we find that our Miramorphic differentials omega zi zj at z just become then omega I j of sigma, which using the same notation is 1 over sigma minus sigma I minus 1 over sigma minus sigma j d sigma. This is something you can easily check from the explicit form here, and I've just plugged in a generic gauge choice for sigma plus and sigma minus here. Okay, so what does this mean for our full integrand? Remember, the reason we're doing this is that we want to calculate the integrand on the nodal sphere now. Well, let's look first at what this does to p mu. Remember, p mu was just 2 pi I L dz plus sum over ki omega zi z naught of z. So just plugging in these two formulas into that, what we find is that p mu of sigma becomes L mu times omega plus minus of sigma plus sum over I equals 1 to n ki mu over sigma minus sigma I d sigma. Now, this is remarkable. This looks like tree level for n plus 2 particles. But notice that L square is still non-zero. It looks as though we set L square to 0 in these equations, but L square is very firmly non-zero in all that we're doing. One way to highlight this point is now to look at the scattering equations. And remember, we calculated out the scattering equations from the residue on the sphere, from the residue at I of p square. And what we find on the torus was that EI1 was ki dot p of zi. So clearly, what this becomes on the nodal sphere is, well, still ki dot p of sigma I now. But if you now look at this in more detail, you find that you can rephrase this as now n plus 2 scattering equations, where I'm using SL2 invariance on the sphere. And these now take the following form. Let my label A run from all 1 to n, but I want to include plus and minus so that this becomes particularly compact. And then my EA1, and particularly also the EI1, take the form of the residue at the marked point sigma A, but not of p square now, but of p square minus L square omega plus minus square. Now, there's nothing magical going on here. I've literally just taken this formula and rephrased it as a residue of something. And clearly that cannot be the residue of p square, because if we calculate the residue of p square for plus and minus, we would get the wrong answer. There's an L square term there. So this term is something that we have to subtract out. But I've really just rephrased what we actually find in the calculation invariant format. Now it should also be clear why we find this. So why do we find this? We started out on the torus by imposing the constraint p square equals 0. But remember, in moving from the torus and applying the residue theorem from the torus to the nodal sphere, we traded one of the scattering equations that implied p square equals 0 for the localization on the boundary divisor on the nodal sphere, on the q equals 0. So from the residue theorem, we traded u equals 0 for q equals 0. So we know that p square is not 0 anymore because we precisely traded that constraint. Instead, we know that p square is still whatever we imposed without the last constraint of u equals 0. And we know that that was just u dz squared. And phrasing that on the sphere, that is nothing but L square omega plus minus square. Okay, let me maybe spell this out in a little bit more detail, because we're going to need this in a moment. So let's look at these scattering equations and spell out what I've just written. So remember what we said on the last slide is we have that for A equals 1 to n, including plus and minus, our scattering equations are now the residue of at sigma A of p square minus L square omega plus minus square, where, as I said, we have also included the nodal points sigma plus and sigma minus in what possible equations we can write here. And if we spell this out, we find that explicitly for the EI, for all particles I equals 1 up to n, we find the following form. We find still the same type of scattering equations. Apologies, I have an additional factor of 2 that I'm going to divide out here. We still find from j not equal I ki dot kj over sigma ij, but now we have 2 additional punctures, and we find that they give us L dot ki times 1 over sigma I plus minus 1 over sigma I minus. And if you calculate out the same for the plus and minus scattering equations, same factor, you will find that we now find the sum over all I equals 1 to n, with a plus and minus here, L dot ki over sigma plus I. Notice in particular that there's no L squared term here, so there's no 1 over sigma plus minus sigma minus in these functions here, which is as expected, because it won't work. If we had included such a term, the equations wouldn't be SL2C invariant anymore. Which brings me to an important point, a few comments. As we must, we recover Möbius invariance for these scattering equations. In fact, I've used Möbius invariance to write down the last 2 scattering equations, the E plus and E minus here. They're now completely rational Miramorphic, and they in particular look like tree level n+2 particles. But remember, we haven't set L squared to 0. There's no cut here. Subtract out the L squared term here. And I should mention that you could calculate now how many solutions there are. So naively, you could assume that there would be now n-1 factorial solutions, which is n-3, well, n, let me write this the other way around, n plus 2 minus 3 factorial, which is what this looks like. But we have some singular kinematics here because the scattering equations have now a loop momentum L that comes once with a plus and once with a minus. So there's some back-to-back kinematics here. So in fact, some solutions here drop out, and you can find that this becomes just n+1 factorial minus n-2 factorial. If you wanted to prove this, you could do so again by soft theorems. Okay, now putting this all together, what we've seen is that the integrand now has this 1 over L square. Remember, that was the U factor which we traded for the localization on the Riemann sphere. We've seen that we find the integral over all punctures up to the volume of SL2C. We haven't been very explicit, but this should be intuitively clear because we integrated over over n-1 of the punctures. So it should be clear that you can trade this into an integral over the n-1 punctures, and you just have to make sure that all the Jacobians come out correctly here. Now, we've also seen that the scattering equations come out like this. Well, I've just used the notation P2 here for P square minus L square omega plus minus square. Sorry, this actually should be a P1 because it is at 1 loop. And the only thing we haven't discussed is what this integrand looks like. And the reason we didn't is that the calculation from what I showed you at the Torus is straightforward, but it is a bit lengthy. So instead of going through the calculation with you, I will just tell you what comes out of it. And you can either trust me or you can look this up in the corresponding references. So remember, we had two factors here, which came with the Pfaffians of the full m's and the partition functions. And we were summing them over spin structures alpha from 2 to 4. Now, if you calculate this out, what you find is that the sum over spin structures 3 and 4, which are the ones that we've identified as the NS states, if you remember, it can be simplified quite massively from alpha is 3 and 4. This is the NS part. And this starts to look like a tree level one with 2 additional punctures, but in the back-to-back limit. So I spelled this out explicitly down here. The NS with an R part that enters into this reduced Pfaffian is just the one where we put in 2 additional particles with momenta ln minus L and identified the polarizations of the 2 particles up to the back-to-back condition. And the sum over R here is done as prescribed down here with the standard delta mu nu, which is just the projection. In particular, this means that if you calculated this out, you could implement the sum over R by effectively replacing all the epsilons that you find by a dot product, except for where they dot into one another, where you would find just a factor of d minus 2. Now, the other part here that I haven't told you about yet comes from alpha equals 2, and it's the Ramon sector. So this corresponds in particular to Ramon states flowing through the loop. And this is defined just as on the torus, but where we had the Ziegel kernels, we're replacing them by this somewhat massive formula, but all the cancel out in the end, and you can pull them out and simplify the whole expression. And for the diagonal entries, just replace P by P mu. Okay, so what I hope I convinced you of so far is that the formula that we find here is now massively simpler. In particular, we're solving just scattering equations that look like tree-level scattering equations with 2 additional marked points. That's certainly no big deal in comparison to the Jacobi theta functions that we had to deal with before. But also these integrands are now, once you pull out all of these square roots and cancel everything, they're just meromorphic functions again. So everything is massively simpler now. And you can see now manifestly that what we were bothered by before, that you couldn't see that the integrand is rational. Now, on the nodal sphere that we find down here, we find that this is manifestly a rational integrand. Now, so what we did today so far is we saw that a residue theorem relates us from the torus up here to a nodal sphere. And what this suggests, well, we haven't seen these calculations, but what this suggests is that at least for type 2 supergravity in 10 dimensions, there is an expansion in nodal spheres instead of genus. Obviously, that would be a massive simplification, and that is something that we would be very excited about. So we'll see some of that in the next lecture. But before we can get to that, we should talk a bit about some other bits, which is that now on the Riemann sphere, nodal Riemann sphere, there's a few consequences for the representation that we haven't seen yet. But also, everything we said right now was for supergravity, or if you want the RNS ambitwister string, which was absolutely necessary, because on the torus projecting out states is nothing that we can do it right now. On the other hand, we have much better control of what happens on the nodal sphere. So what we're going to see in the next lecture is how we can extend this from supergravity also to other theories. Okay, and I think at that point, I'm going to wrap up and we'll take a short break and I'll see you back in a few minutes.